Okay, grade 12s. What we're going to do is we're going to be starting on a new physics topic. We're going to be looking at electricity as our topic for the next little bit. And we're going to start electricity for Lou. This video is especially for Tatum. Hi. This video is especially for Tatum.
And Kristen.
Hi.
We love you.
Love you.
Come to school.
They love you too. Right, so we're going to be starting with electricity and we're going to start it from scratch. As if we haven't done electricity before, almost. Okay, not completely because we did it since grade 10. So we're going to be starting off with that and we're going to go all the way through to the idea of EMF, internal resistance of the battery, etc., etc. We're going to be playing around with circuit boards as well during this time because the topic for your term 3 practical is electricity and internal resistance. And I'm going to demonstrate that for you because the chances of us getting a question that is linked to that in our physics paper is really high. So we want to make sure that you've actually seen what the prac looks like. Okay, so when we talk about electricity, let's talk about some basic concepts first. When we started off, one of the first things we would have spoken about in grade 10 is the idea of charge. Okay, so we would have spoken about charge and we would have learned how to calculate charge as well. So when we spoke about charge, the unit for charge is considered to be the coulomb, and all a coulomb is a lump or a group of electrons. Yes? So instead of talking about the movement of just electrons, we talk about the movement of charge, which means the movement of lumps of electrons, bunches of electrons. Okay? 1 coulomb is the amount of charge passing through a point in a circuit in 1 second when the current of 1 ampere flows in the circuit. So to calculate the this particular physical quantity, we use the Cotte equation, which is Q is equal to I times T. And as you can see, I have a bit of an issue on my thingy, So according to this, charge is Q, I is current, and time is delta T. So that's my Cotte equation, and we've used that in a whole bunch of examples back from grade 10. I don't think we dealt with it in grade 11. When it comes to time or calculating time, remember we must work in seconds. Okay? It's not often that we get asked questions like this in a grade 12 paper, but I find that it's quite useful to have this tucked away somewhere, because sometimes they ask you something quite random, and if you don't have this as a basis, then you feel lost when actually it's quite simple. Okay? So that's the idea of charge. Then when we talk about current flow, now when we speak about current in a circuit, that's the movement of the electrons that we're talking about. So current strength is the amount of charge moving through a certain point in a circuit in 1 second. That means that if we're standing in the circuit and we're measuring the amount of charge moving past, if we take how much charge moves in 1 second, we refer to that as the current in the circuit. Okay? Think of it as if you were standing on the side of the highway watching cars moving past. That would be sort of what current is. And an ammeter, which is something that measures charge, would be that thing watching how many cars went past or how much current is going past. The symbol for current is I. We know that. The unit is the ampere, not amps, just capital A. Okay? And the formula we use is this one. This is not the Ohm's law one. This is simply the Cotte equation that has been moved around. Okay? You should be fine with it. Alright, then potential difference. Now we're doing potential difference as an overview, and then later on when we talk about internal resistance of the battery, we'll go back and we'll talk about EMF and potential difference again. For potential difference, remember, potential difference between 2 points in a circuit is the work that must be done to move 1 coulomb of charge from one point to another. What that means is, if we have a resistor, we usually calculate the potential difference across the resistor by taking a voltmeter and reading from one point to another point. Agreed? And that voltmeter measures the energy at this point compared to the energy at that point. Potential difference means how much energy is required to push or force the electrons through this component. What does it take to make the electrons move through the resistor? That is described as potential difference. If you guys think about, if you think about an obstacle race, you guys know what an obstacle race is? A race where you've got to climb a wall or do something, okay? If you think about it, it takes more energy to go through an obstacle than it would to run the normal course of a race, right? Which is kind of the same idea with potential difference. That it takes energy for the electrons to move through that particular component, whether it be a light bulb, whether it be a resistor, whether it be whatever it is, okay? So when we talk about potential difference, it's the difference between these 2 points, and it tells us how much work must be done with energy supplied in order to move the electrons from one point to another in the circuit. Okay, makes sense? This bit that talks about work done or energy supply is really, really important, because there is a very close connection between work done and energy required. We all have read the back of food packets when it comes to kilojoules, yes? Or kilocalories. That tells us how much energy that food supplies to us. It also tells us how much work we can do if we are fueled by that food, right? The connection between energy required and work done is very simple. If it takes you 200 joules of energy, if you use 200 joules of energy to get up the stairs, to get from the ground floor to my classroom, it usually means you've done 200 joules of work to do that. So the amount of energy required translates to work done. Okay. Now, the symbol for potential difference is V. Of course, the unit is the volt. And the formula we use states that the potential difference is equal to the work done over the charge. Another very, very important equation that we need to put into our bag of equations that we can use when we're solving electricity problems. Okay? Remember, W refers to the work done or the energy required, measured in joules. Okay? And then charge, of course, is Q in coulombs. Okay. Resistance. Notice how we've just looked at current, we've looked at potential difference, and now we're looking at resistance. So we've been looking at I, V, and now R, which as a whole refers to Ohm's law. Do you remember this? So we'll look at Ohm's law in a little bit, okay, which is the relationship between these 3. When we talk about resistance, what's really important is for us to realize that every component within a circuit will offer a certain amount of resistance. And that's not just the bulb or the light bulb. I said bulb. The resistor or the light bulb, okay? We're talking about everything. So the wires offer resistance. The battery offers resistance, okay? The resistance, simply put, is the opposition a conductor offers to the flow of charge. Conductors have varying amounts of resistance. If we compare different conductors, what sort of conductors do you guys know about?
Electrical.
Like, yeah, what sort? What were they made out of? Copper. What else? Nichrome.
Yeah.
Is nichrome a very good conductor? No. So nichrome, because they use it inside of a bulb, is not a very good conductor. Okay, we know that it offers a lot of resistance to the flow of charge. What's the best conductor out there?
That's H with a TE.
Tungsten.
Yes.
Yes. Also not great, eh? Tungsten wire. Not a great conductor. Offers lots of resistance. Copper wire is good. What's the best conductor?
Gold.
One of the best conductors is gold. Absolutely. Why don't we use gold in all of our conductors?
Expensive.
Expensive, and if they are stealing cables for copper, what would they do if the cables were made out of gold?
Now, but you know, they said there's a lot of gold in the ocean for everyone in the world to have, like lots of it.
Okay. I don't know what I'm supposed to do with that. No, you're right. Okay. Okay. Where do we use gold most often in terms of electrical stuff? Computers. So when it comes to computer circuit boards, They use gold for the tracking, okay, because the conductivity is so good. Okay, and you need really good conductivity with very little resistivity when it comes to tracking inside of, you know what I'm talking about, the little lines inside of it. Why are you just saying no, Bolu?
He doesn't break things.
Have you ever broken your remote over?
You just want me.
Hmm?
You just want me.
I know. Are you not over it? And are you going to talk to them now? Yes. Okay. Let's pause there.
It's over.
So when we talk about resistance, we're talking about the opposition of a conductor or the opposition that a conductor offers to the flow of charge. Do you guys remember the factors that affected resistance back from grade 9? Go, give me one.
Temperature.
The heat. So the temperature.
The length.
I'm just going to talk about temperature first. If we talk about temperature, the hotter a conductor is, the more the particles move, which means the more difficult it is for charge to move through the conductor, hence resistance is increased. Next one you said? The length of the conductor. The longer the conductor is, the greater the resistance will be. Next one?
Material. The material.
Material and diameter, I will accept both of those explanations. So if we talk about the diameter, the wider the conductor is, the less the resistance is. Because if we make the conductor wider, there is more of a pathway for the current to flow. However, if we talk about type of material is inherently or innately connected to the way that material is made, okay, physically. And so certain materials conduct better than others, like we were talking about gold being a great conductor versus tungsten being a poofy conductor. All right. If I now look at how to indicate resistance, we use an R, the symbol is an O, and 1 ohm is considered to be 1 volt ampere. The reason an ohm is considered to be a volt ampere is because if R is equal to V over I, then it's volts over current, which is the same as a volt ampere. Okay? And then, that is the equation that we use from Ohm's law, where R is resistance, V is potential difference, and I is current strength. Alright guys, so our definition for this in terms of Ohm's law says that the current flowing through a resistor is directly proportional to the potential difference across the resistor, provided that the temperature remains constant. Now, obviously, the temperature remaining constant is linked to the idea that temperature has such a huge effect on the resistance of a material, which is why whenever we do pracs in class for resistance, we're never going to get great results because we can't control the temperature. Okay? So there's going to be an increase in temperature when we use circuit boards, which is why some of the times the results are a bit funny at school. Okay, now, if we look at ohmic and non-ohmic conductors, remember we did this in grade 11. We spoke about conductors that obey Ohm's law and ones that do not. Okay? If we talk about an ohmic conductor, we're saying something that obeys Ohm's law. V is proportional, remember the proportional sign to I, provided the temperature stays constant, which means that the ratio of V over I is always constant. And a non-ohmic conductor means that it does not obey Ohm's law, which means that the resistance is not constant. So as the temperature increases, as the resistance increases, as the temperature also increases. That means that most of our conductors are actually non-ohmic conductors, because as the temperature increases, the resistance increases as well. Okay? Alright. And then, in terms of what the graphing looks like, we've seen graphs like this. An example for an ohmic conductor would be nichrome wire, and then one for a non-ohmic would be a light bulb or an electrolyte solution. Okay? And that is where I'm going to stop for the day.